Today, we are going to talk about optimum filter in digital communications. In our digital data transmission, where binary 1 and binary 0 is being transmitted through any one of the digital modulation techniques, the signal which is being received at the receiver along with the noise, white Gaussian noise. So the receiver, which is to be optimum so that the probability of error is to be minimum at the receiver output. So that signal which is received with the optimum receiver, which is called optimum filter, with the minimum probability of error. Analyze the optimum filter. What should be the condition for optimum filter and for the designed probability of error which accepts a minimum value of the probability of error, then we can say that that receiver or an integrator which can be optimum. So then what is the condition for that transfer function of that optimum filter, and what is the minimum probability of error of that optimum filter, such that we understand what is the optimum filter. So this is where we can say the block diagram of the filter as a linear time invariant property of the filter having the transfer function of h of t. Considered to be a filter, we derive that this filter to be optimum, such that the output would be the less probable or minimized probability of error, which gives the maximized output. So that is what the optimum filter. So this is where the filter, we have the output as the input of signal x of t assumed to be signal plus noise. So you take it as a Gaussian noise, okay, and this x of t is nothing but the signal g of t plus Gaussian noise w of t, and the output y of t is signal plus noise, so that this would have the output of signal plus noise. So in frequency domain we can have the product, so which is sampled at t equal to t seconds. So that is what Gaussian noise we have taken signal, and this is where the output, which is signal plus noise, where x of t is the sum of these signal g of t plus w of t, and then the output y of t would be the output signal we termed as a g naught of t, and the output noise termed as n of t. Y of t is sampled at every t equal to t seconds, then y capital T, that becomes g naught of t at a capital T plus n of t, or n naught of t. So this is where the output y of t, g naught of t plus n of t, sampled at t equal to t seconds, that we can measure the maximized output, the signal power by instantaneous noise power, the instantaneous noise, the signal power to the noise power mean square value, that is what output noise power, the signal to noise ratio, power ratio, which gives signal to noise ratio. The output is maximized such that we can estimate where to find out in case of g naught of t magnitude of square divided by mean square of this noise, This is what noise power. We would like to find the signal power from G naught of t. As you know that G naught of t is the product of input and transfer function of this in frequency domain. So as we said that G naught of t, G naught of t is okay, G naught of t convolved with h of t at this function, and G naught of f we can take it as G of f and h of f in the frequency domain. So that is the output G of f and h of f, and now the inverse Fourier transformation of this G naught of f is G naught of t is nothing but integral minus infinity to infinity G naught of f e power j 2 pi f t df. This is what the output sampled at t equal to t seconds G naught of t, that becomes we replace t equal to capital T, and we want a squared magnitude, so that squared magnitude will find out squared magnitude of this. And then as we know that squared magnitude of the output signal power is this function product of h of f and g of f e power x j 2 pi f capital T df, magnitude of square integral minus infinity to infinity. So where the noise power, average noise power, that is being calculated, power spectral density, output power spectral density, this is what minus integral minus infinity to infinity Sn of f df. So integrating this output power spectral density, we will get the noise power, average power. This is nothing but we understand Sn of f is squared magnitude of this transfer function multiplied with input noise power spectral density, input power spectral density. So the input power spectral density of noise is Sni of f. So this is the property, multiplying with a squared product, squared magnitude of the transfer function, we will get the output power spectral density. So we integrate that, we will get the noise power. So this is what the integration. The ratio of these two can be written as simply like this. The same thing, the expressions, the signal power by noise power. This is expressed in terms of power spectral density because it's a Gaussian noise. Now we can simplify this as this numerator term. This numerator term can be simplified as the product of squared magnitude, this integral function, using Schwarz inequality condition. Schwarz inequality condition is the one of the condition in mathematics where these two functions, complex functions, is less than infinity. So this phi 1 of x and phi 2 of x are the complex functions. So integral phi 1 of x square dx less than infinity, phi 2x square of dx less than infinity. So this product of these complex functions phi 1 of x, phi 2 of x dx magnitude square can be taken less than or equal to. So the sum, the squared product is less than or always less than or equal to individual product of individual squares. So this is the phi 1 x of square and this is phi 2 x of square. So this is what integral functions, the product of individual squares. So always this term is greater than this product of this squared product of this. Okay, so that is how the Schwarz inequality. Now we can assume from this above condition of this we assume the product of phi 1 of x and phi 2 of x, where out of see here in terms of see here yeah, g of f and h of f and e power j2 pi f t is the product phi 1 of x and phi 2 of x can be taken as phi 1 as root of Sni of f, that is the input power spectral density of noise. This term is adding, multiplying here, h of f here, h of f, and here in g of f the remaining term g of f e power j2 pi of t divided by root of this Sni of f. So that is how it is taken as the product. So like here Sni of f under root h of f is the phi 1 multiplied with g of f e power j2 pi f t divided by Sni of f under root. Okay, so this is multiplication. Okay, so this is phi 1 and this is phi 2 of x. So that is how, because of this Schwarz inequality condition, we can write it back squared magnitude, this is less than or equal to squared magnitude of this, so that square, this becomes SNIFF, and this is also SNIFF in the denominator. So the remaining term, the square, and in the denominator is already there average noise power. Here integral minus infinity to plus infinity h of f square SNF df. Okay, here now this term gets cancelled, this term and this term gets cancelled, and now then this is the way simplifying the integral function in the numerator by simply considering Schwarz inequality condition, separating it to two factors. So this is obviously getting in terms of g of f 2 pi f t or magnitude of the square by SNIFF df. So magnitude, always this phase term can be nullified, and this is the magnitude. The magnitude integral minus infinity to plus infinity GAFF square SANF df. So this is the signal to noise ratio. This would be maximized once that would be taken, considered as a optimum filter. So this is normally the input power spectral density of any Gaussian noise, and this is the squared magnitude of this input signal. This is what energy you can consider. So my integral minus infinity to infinity, this function is taken as SNR of optimum filter. This can be maximized, to be maximized. So in this transfer function to be maximized, so that for maximizing SNR, the equality condition is another one in Schwarz condition. The equality condition satisfies that these complex functions phi 1 of x equal to constant times of conjugate of second function phi 2 of x. Already we considered as phi 1 of x as this and phi 2 of x is this. Writing down by satisfying this equation, so this becomes h of f equal to constant time conjugate of that g of f star e power minus j2 pi f t, and this root of SNIF Divide by this root of SINF becomes SINF. So this is what transfer function h of f. So the optimum transfer function to be maximized where equality condition satisfies the maximized condition, maximized output for the transfer function of optimum can be considered as k g star of f e power minus j2 pi of t divided by Sn of f. This is the transfer function. So this transfer function can be termed as, can be taken into consideration for getting maximized output when the signal and the noise is given. That filter will give the optimum output such a way that that transfer function of that filter satisfies this condition.